Hey, Matt Matherson here with Math Madness. Thank you so much for joining us and being a part of the program today. We really do appreciate it. Well, we are concluding with the L'Hopital rule. This is our third and final episode on the L'Hopital rule. And we know that we have certain conditions when we're dealing with L'Hopital, right? It's got to be an irrational function. These limits are not cooperating. We were dealing with undefineds or indeterminates. There's all kinds of different situations with these limits that cause us problems. Hence, L'Hopital rule to the rescue. Let's look at our third and final setup here when we can utilize the L'Hopital rule. We started off with, remember, positive negative infinity over positive negative infinity was our very first case. Then our second episode, we said that if something is being undefined, such as being divided by 0, we can use L'Hopital's rule. And for the final one here, we've got a 0 being multiplied by a plus or minus some indeterminate, which today is just going to be an infinity, but there are other situations where you have indeterminates as well, like say 0 being raised to the 0 power would be an example of another situation like that. But today we're just dealing with this because this is going to be forcing us to deal with a product that needs to be transformed into a rational function. And so that's a good segue for me to introduce the problem here that we are tasked with finding the limit of today. Okay, well, you've heard me scream probably about this. It does have to be a rational function, and you can see that this is anything but a rational function, right? Okay, well, let's see what we're dealing with here. We have the limit as x approaches 0 plus. That's the first thing we probably want to address, isn't it? What does this 0 plus mean exactly? Well, let's go ahead and just kind of draw that out for a second. We know what we're dealing with on the coordinate plane, right? We've got our y-axis here, and I've got my x-axis here. Well, our ln of x function is going to look something along the lines of this, isn't it, right? Because we know our exponent is just the exact mirror opposite of it. So, and again, this is just kind of a crude drawing, but this is pretty much what we're dealing with the ln of x. And we're saying that we're approaching this from the positive side. That's what this means. We're coming from the positive side towards 0. Yes? And if we look at our function here as we're approaching 0, what seems to be going on with it? Right, it's going down, 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 down into the negative infinity category. And so what can I do now? Well, I can recognize that the ln of x is a negative infinity is what I can do, all right? So now that we've got to look at our graph here, we know what we're dealing with. I'm going to go ahead and erase this so we can go ahead and work out this limit. But I just wanted to show you exactly so you get a good visual of what we're talking about here. We're approaching it from the right-hand side, the positive side, all right? If it were negative, we'd be approaching it from the left-hand side of the coordinate plane. Okay, well, we've got the ln of x taken care of. What about the initial x here? Well, x is approaching 0 in our limit here, so that means this x is approaching 0. All right, well, does that look something along the lines of the third one here as far as 0 being multiplied by a plus minus negative infinity? It most definitely does, doesn't it? So I can now say that we will be utilizing Monsieur L'Hopital, right? Don't think I can't speak French. Well, that's about the French that I can speak. Okay, well, that being said, let's look at this real quick. And how are we going to find out the limit of this particular instance when we don't have it in fraction form? Well, there's a good answer to that too. So let's just go ahead and acknowledge that we are taking the limit as x is approaching 0 plus from the positive side. We have been working with fractions. So in order to make this a fraction, I'm just going to take the more complex fraction and put it here in our numerator. Our ln of x is going in our numerator, okay? Well, what about this x here? Well, we know that there's an implied 1 under it, don't we? Yes, x being divided by 1. So in order for us to make this equivalent here, when we turn this into a rational function, I have to invert this, don't I? Yeah, so let's go ahead and put our 1 over x. Well, we remember how we've solved these for the past couple of episodes, right? We just take the derivative of this mess to create some new messes that we can take the limits of, right? Well, let's go ahead and find the derivative of these particular values right here. We've got our value of limit as x approaches 0 plus. What is the derivative of ln of x? Well, we've gone over that a few 100,000 times right now, haven't we? And that's just our 1 over x. Okay. Well, what is the derivative of 1 over x? This one you may not be familiar with, and that's okay. That's what we're here for. So the derivative of 1 over x is just a negative 1 over x squared. Yes. Yeah. And I tell you what I will do. I'm going to prove that the derivative of 1 over x is negative 1 over x squared right now, because that one probably would help you guys a lot. So let's go ahead and take the derivative of that. I'll prove it right now. Let's go ahead and take our f of x here as a function, and it's what? 1 over x is what we're tasked with finding the derivative of. Or I said I'm going to prove it. So fine. Let's understand, though, that the x in the denominator here, we have an implied positive 1, don't we, right now? So I'm going to get this out of the fraction form so that I can take the derivative of it. So in order for me to do that, what am I going to have to do? Well, right, we're going to have to invert that again, aren't we? So I'm going to bring this x up over the vinculum, the division sign here. But when I do that, what's going to happen to this positive 1? Right, it's going to turn into a negative 1. That is how we made that transformation out of the fraction form. So now I can find the derivative of that, right? I can take f prime of x, and I can find the derivative, which is going to be what? Well, I'm going to bring the negative 1 down. We know that, don't we? And now what happens? Well, we know with our derivative formula, what is that? X to the n minus 1 dx. Yeah, what is our n in this case? It's our negative 1. We have to subtract it by 1, giving us a negative 2. All right. Well, we could leave it in this form if we wanted to, but I am proving that this is a fraction. I'm proving that the derivative of 1x is negative 1 over x squared. So I'm going to put this back into fraction form. And what is that going to look like? Well, it's going to look something along the lines of just negative 1 times. I'm going to put this back in fraction form, making it 1 over x squared. I am dropping the negative in the exponent, right? Because again, I'm inverting it. So that's going to give us a negative 1 multiplied by 1x squared, isn't it? All right. Well, anything multiplied by 1 is what? It's just that value. And we know that this is a negative. So I've got negative 1 over x squared. What did I say? The derivative of 1 over x is the 1 over x squared. Negative. I didn't put the negative in there. Okay. Well, we have proven that this is the correct derivative. So now what can we do? Well, we want to simplify this, don't we? Because we do have a complex fraction. We've got 1x being divided by a negative 1x squared. How do we deal with dividing fractions? Right. We just take the inverse. We multiply it, don't we? So I'm going to go ahead and simplify this out. And that's just our 1x is being multiplied by, I'm just going to go ahead and invert this, right? It's going to be a negative, we know that, but it's going to be an x squared over 1. With me so far, okay? All I've done is just flip this bottom denominator and make it, it's still negative. I've just flipped this value, x squared, and it's over 1. I'm just going to multiply this out now, right? So 1 times a negative x squared, we know this answer is going to be negative, and that's just going to give us an x squared over, well, x times 1 is what? It's just x. All right. Well, that's easy enough, isn't it? Well, I've got an x squared being divided by an x. I can just go ahead and cancel one of these x's, can I? Leaving me with a negative x. All right. Well, this is shaping up rather nicely, isn't it? So now this whole mess right here, this complex fraction, when I take the limit of it now, as x approaches infinity 0 plus, it's now negative x, isn't it? Which is equal to, if I plug in my 0 now, right? I've got my 0 here. If I plug my 0 into x, that just gives me a 0 here, yes? But a negative 0 is still a 0, and that means what? Yeah, it means that this whole limit crashes to absolutely 0. L'Hopital rule, again, to the rescue, making this much easier to work with than what it could be. Well, thank you so much for joining me for this 3-part series on L'Hopital's rule. I hope it's been informative for you. We're going to see you real soon. I'm Matt Matheson. This has been Math Madness. Have a wonderful day.